Okay, so this is like a sample problems that lets us get started with a big topic, and kind of we run through things fairly quickly, but it is actually quite an accomplishment of how far we got, starting with nothing but this mixture problem of mixing coffee. So the equation that we formed, we certainly passed that, but that certainly will still be it is a challenge, and it still will be tested on it, possibly setting up systems of equations. Okay, so that's a skill that is absolutely essential. Even though now you pass that, and then we totally leave it behind, and we're doing algebra purely. So that's what happens afterwards. We're looking at our two equations, which we then rearrange in such a way that both the unknowns and the x and y are aligned under one under the other. Coefficients are clearly visible. The first pair of coefficients refer to the Kenyan coffee, and the other one, 1 and 3, to the other Colombian coffee, and then the blend on the right. Okay, in the meantime, both equations refer to their x and y coordinates, and they refer to two very different things. Components rather refers to, what is it, to weight, right? So this is weight, and this is price. So as you can see, well, that realization is actually quite a challenge. A realization that we form a vector. If we look at 614, for example, or 1, 2, what is the x and y components of those two vectors are really unrelated to each other. It's not like location, x and y coordinates in space or something like that. They are not, and do not have to be related to each other. Okay, so that is if you look at each vector in a horizontal manner. So so those two numbers are not related in any way, unit-wise or anything like that. So that's how you end up with linear equations of any size, because you just pile up data in it, and the data might be of any nature, well, to be determined later. Okay, so we're trying to make it into a single equation of single vector variable. Okay, so we made that step. The intermediate step was made next, where we realized that x and y are simply the coefficients of the two vectors, 1 and 2, as you can see, and 1 and 3. They are multiplied by x and y. Okay, so that already creates a single vector. So that's one major advancement right here, that we turned two equations into one, made of vectors. And then this is a major transition that I would like to explore a bit later in a minute. This transition. So once again, this transition from geometry to algebra. So that's the big one. And then the next one is the actually seeing matrices. But for the time being, yeah, so let's go all the way to review our solution. So as you can see, we're looking at the multiples of our two vectors. So once we identified 1 and 2, 1, 3, then we know that x and y serve as their multiples, and therefore we are looking at the sum of two vectors when we allow x and y vary, and that produces that effect that we see on the right, which I will illustrate again in a minute. I just want to go through this all the way. We are seeing here, finally, a matrix is formed. So that's the second major advancement, is when we realize that we actually those two vectors are not, they don't live separately, but rather they form those two vectors. They serve as two columns of a matrix. Okay, so we're trying to build a function, and it turns out that there are 4 numbers involved. And then we just, for convenience sake, we put them in side by side. So 1, 2, and 1, 3. What do we do with them to put them together? Well, I'll just make a table of them. So that's the table over there that we're looking at. So columns. um, so those two vectors that are marked here, they are 1, 2, and 1, 3. They are columns. So columns. Okay, and then this is at that point we sort of stopped. We made one more observation. We did not stop. We kept going because there's so much going on here. So the next step was to realize that all of this, whatever is happening to this so-called matrix, is the dot product. So the matrix x, the vector xy gets a dot product multiplied with each of the rows of the rows of our matrix, and that each of that multiplication produces a number, one single number, and that number ends up in the right hand side. Okay, so the input is xy, two numbers, one vector. The output is b, on the right, two numbers, one vector. Okay, so before we start over, look into details, this is what we end up with. So that is the crucial observation, is that we actually, this is a typical notation that you see at the bottom, not a typical standard notation, but however I want to put something here to make a point, put parentheses around x to emphasize that x, so we're talking about functions. A is the name of the function, x is its input, and b is its output. Okay, so all this work compacting together those numbers into vectors and later into matrices produces nothing but a function, and that function is, and we're trying to solve this kind of equation. We're trying to sort of reverse the operation. So x is the input of A processes x and then produces b. Okay, so that's the direct way, but usually it's that's what algebra, any algebra, not linear algebra necessarily, but any algebra that you see, it goes in the opposite direction. You know what the output is. Find the input. So we need to find x from b. Okay, so that's the typical what it means to solve an equation. The fact that we're now talking about vectors rather than numbers doesn't change anything. The story is still the same. We have a function, we have the output of the function, and we need to find the input. We have to work backwards. So for example, that's how the logarithm was invented. So I have a function, 2 to the x is equal to 8. So I know how the exponential function works, but I need now to reverse it. So I know the output is 8. What is the input? Okay, so if it is 8, you can say x is equal to what? 3. Okay, but imagine that I have 2 to the x is equal to 7. Then what do? You have to invent this function called log, and that's roughly what we will be trying to accomplish. How to reverse the operation of a function in order to solve the equation. So just happens to be a whole bunch of vectors there. Okay, so it is. It happens to be x and b both are 2 by 2 vectors, or not 2 by 2 vectors, but rather just two-dimensional vectors. Both of them are in our R2, but it doesn't mean that it will always be like that. So there will be high dimensions to begin with. We'll get to that, but right now it is actually better to go backwards and see lower dimensions, and that's what we started doing here. And so what happens to this stuff when we go to lower dimensions, the one that we have examined already, and what if we have one equation, wait a minute, two unknowns, one equation. That's what we're looking at right now. Two unknowns, one equation. Like this. Okay, so we're talking about a function from R2 to R. Okay, so it is then, its graph is a plane, as you might, I'm sorry, a line. No, it is a plane. Yeah, it is a plane, but this is a line. This is a line. Okay, so one equation. My function is, where is my function? This is my function. It is still a matrix from R2 to R. Where is it? This is it. This is my matrix A. It just happens to be 1 by 2. It was 2 by 2. This is my where is it? Here's 2 by 2 matrix in the previous example. So A is equal to 1, 2, 2, 3. It is a 2 by 2 matrix. Okay, but that is only because we had two equations to unknowns. But if we go to lower dimensions, for example, we can be in this situation when there is only one row and two columns. So that is a 1 by 2 matrix. And then as you can see, it is still what happens. You carry out the dot product multiplication mn times xy, and well, let me put the specific numbers here so that it would match what we have. Say 3 and 5, 3 and 5, and then the right hand side is still an unknown. Say well, it still is known. Say 5, 2, whatever. Okay, so then this is a line, and then it's kind of an unproductive problem, that because it doesn't have any good solution. It is in fact just one line and one equation, one line. So there is nothing to be solved really. All you can say that if x and y satisfy this equation, they are solutions. If not, they're not. Okay, but as far as the idea of a function present here, it still works out. It just happens to be given by a matrix which is 1 by 2. And then there was another one when everything is flipped and there is only one input variable. So here's I'm having a matrix 2 by 1, say 2 and 7. Okay, so I'm talking about the matrix from R to R2. So the dimensions are, instead of 1 by 2, they're 2 by 1. Then the input is a single number. See, this is 1 over here. Dimension is 1. And so how does it work out? It's once again a matrix. It just happens to be, as I put it here, happens to be a very a smaller one. If the previous one was a single row, this one is a single column. But the rest is the same. Still, the idea of the dot product is fully applicable, except, well, this time there is really no vector multiplying by vector. So, well, what is the answer? 2, 7 multiplied by x. What do I get?
2 times 7 is 14.
No, you don't multiply 2 by 7. It is a multiplication of. Well, actually, I don't want to confuse you and say this is the dot product. This is dot product, right? But this is not dot product. It's scalar product.
So is it like 9x?
What?
Is it 9x?
No. The output should be a vector. 2x and 7x. The output is a vector. The input is x, is a single number. It's multiplied by 2, 7. So a vector multiplied by a number. And the result is another vector, 2x, 3x. Okay? This one is also a line, by the way. It is just given in a different way. It is what is it? It is a line given by its direction vector. What's the direction vector? 2, 7. Okay, so this is once again something that we just talked about. So once again, this is not a very interesting system of equations because what is that we have? We have two equations with the same variable. There's only one variable, two equations, the same variable. So if this is, for example, equal to 31, then we are, you can see it, what's the answer? If I try to solve this equation, I have 2x is equal to 3 and 7x is equal to 1. What's the answer? There is no answer. There is no answer. What we're looking at here is we're trying to find we're trying to find out whether or not this line passes through this point, and it doesn't. So there is no solution. There's a point at 3, 1, and there's this line that passes through the origin and with the direction vector 2, 7, and it never passes through 3, 1. It would pass only by accident. So if I put there 2 and 7, for example, or 4 and 14, then that would have been there would have been an answer. So as you can see, the situation is just not as interesting. But generally, we still want to take that into account just to cover all the bases. Okay. So that's just how matrices work out. But I want to trace back and maybe just do much algebra once again. We encountered that before. Let's do numerical things. So there's this transition that I want to explore a little bit more. And specifically what I'm talking about, these are each of the equations is a line. So the line, then to solve the equation means to find their intersection. That's the geometric interpretation. So we could just as well do it with no difficulty, but let me just maybe pick numbers that are more manageable. So suppose I'm looking at the equation 2x plus 3y is equal to 5, and x minus 5y, 1 minus y is equal to 1, something like that. Okay, and then I make that transition that I just discussed into a vector equation, still no matrices, and then what I'm looking for, x 2 1. Hold on, I'll make that transition in a minute. Let's just look at this first. So this is one line, another line. Solution is the intersection. Well, let's just take it slow and let's just draw it with Excel, right? So how? Just the way I did it before. So what I'm going to be doing it. How should I do it? I guess I'll just go for expressing x in terms of y. So just to keep it simple, so I'll have y is equal to I think I want to use this opportunity to do once again the straight lines. It's a big deal, and representing lines as with direction vectors. So what we're talking about here is the line which is what is the line? Let's just keep it simple. So y is equal to 5 halves minus 3 half y, right? Third, that's not right. Y is equal to 2 thirds negative 2 thirds x plus 5 thirds, right? Yeah. Okay. And the other one, y is equal to 1 minus x, or negative x plus 1. Okay. So I can easily plot these as functions of x just to see how it works. So I'll put x here, y1, and y2. Well, let me put x here. Let me repeat x. Okay, so x is starting with, say, 0, and so equal to, doesn't really matter. We don't need to plot a straight line. You don't need a lot of values. So it is equal to the previous one plus 1, and here, what is the equal to, what's the equation in terms of x? So these are x's. So what do I get? What's the equation?
What?
Negative 2 thirds, is it? negative 2 over 3, negative 2 over 3 times x, which is this, and plus 5/3. Okay, 5 over 3. Okay, so that's my equation, and it goes on for as long as we like. Maybe. Okay, so some kind of a line. Okay, and so that's one line. I can plot it easily. Insert scatter plot. Okay, one line. Okay, and then I could do the same, just with a different formula. So I'll put, what's the other formula? Negative x, is it? No, wait, is it? I wrote negative, but I think it's, there is no negative. It's positive.
Yeah, it's x minus 1.
It's x minus 1, right? Okay, x minus 1. X minus 1, sorry about that. So x minus 1, so it will be simply equal x minus 1. Okay. Okay, so let me add, where is that select data? Okay, add, doesn't matter. This is the data. Ah, crap. X values, no, that's not the way. These are the x values. And these are the y values. It's more complicated than worth it. Okay. Two lines, they intersect. You see the answer here somewhere. So the meaning of the intersection of the solving a system of two equations is find the intersection of the lines that they represent, and you can be pretty much very accurate here. I could improve the quality if I make my step of x smaller. For example, what do I do? How about I put a 0.1 here instead of 1? So there will be, that's too small, 0.2. Okay, so they will be closer related to each other. So, well, you can actually, the point being is that you can actually find, the value in the table. The solution might be somewhere in the table. Okay, so see, well, by accident obviously, but this is the answer, and you can see 1.6.6. You see that reference point over there, so it refers to a particular row of our, in fact, this is the row of intersection, right? 0.6, 1.6, 1.6, 0.6.6. So that's the answer, and we solve the system of equations numerically by examination and then just zooming in. So that's what we did. Okay, so that's fine, but that's not how we do it as we move to the next stage. Okay, so the next stage being a vector equation. So let me carry out that step, turning this into a vector equation, which is 2, 1 x plus y times 3, negative 1, and it is supposed to be equal to 5, 1. Okay, so once again, this is called a linear combination. Of these two vectors, and we're going to be using that terminology a lot. And so, and x and y vary. Okay, so the one example that I showed you is here on the right, somewhere. On the right, yeah. right here. So as you can see, you stretch one vector by some factor. So I stretched the first vector, the orange one, by a factor of 3, and I stretched the other one by the vector of 2. Okay, so except, so that's what we could do, and we can, any kind of factor is allowed, and we every time we have a parallelogram of different dimensions, but that's not what we are trying to accomplish here. We're trying to accomplish the opposite. We're trying to find, we need to find x and y. So we need to find an appropriate linear combination. So we're not doing vector matrices yet. So we are thinking of x and y as just simply multiples, and we need to stretch the first vector appropriately and the second vector appropriately, so that together that linear combination will give us exactly vector phi 1. Okay, so I have another visualization here. So, and that's what we're looking for. If you look at what's in orange there, I think we still can make it bigger. No, not orange, that's a yellow. So what's in yellow there, it refers to the picture on the right. And you're seeing 4 vectors here, but really the green and red are A and B, B and A. Okay, so these are the 2 basic vectors that we're starting with. So let me maybe mark it here. So we're talking about XA plus B plus Y, B is equal to D. Okay, except there is a, well, let's just say it's C. Okay, so we are looking at, it is equal to C, but has to be equal to D. So vector D is given, vectors A and B are given, D is also given, and we need to find proportions for these 2 vectors in order to produce the vector D. The vector D is in orange. The linear combination that I have here, see the numbers here, x is 1.5 and y is 1. Okay, let's copy the information from this, so that we would be referring to the same exact situation. Okay, so so it comes from here. What are the vectors? 2, 1, and 3, -1. 2, 1. Oops. 2, 1. I guess I'll just type it. 2, 1. 2. The first vector will be 2 and 1. And the second, what's the second vector? 3, -1. 3 and -1. Okay, so 2, 1, 3, -1, there are the 2 vectors A and B. The coefficients here I chose 1 and okay, I see. My vector B is invisible because it's below the x-axis, so I'll have to fix that in a minute. Which one? Edit, no. Plot area. Okay, so, oh my. Oh, this is complicated. Horizontal axis, no, I need vertical area, vertical. Let me change everything every time.
I think it was just there, like that drop down arrow you clicked on.
Yeah, I did for my plot area, and then it doesn't take you anywhere. It takes you to, maybe it's here. I need the vertical, not horizontal. Vertical. Okay, vertical axis. Okay, so where is it? Vertical axis. That's what I did. I clicked on it, and then it takes me. There is a setting somewhere, and now I cannot find it. Yeah, where is it? Format chat area. I don't think so. Format axis, and where is? Okay, let me try to click on the axis. Okay, here it is. Maybe. You see values, begin, join, the numbers, the values, the values for y. So I created the spreadsheet on the older version of Excel, and now, as you can see, things have changed.
If you see those shapes below axis options on the side.
On the here, no, I don't see any.
Above that.
above, so one of these?
Yeah.
Size and properties. Vertical alignment, no.
Just clicking on axis options right there, that drop down menu doesn't do anything. Right above the shapes on the sidebar.
Shapes, where are the
Right above the shapes, yeah, that, clicking on that drop
This-
down arrow.
This one?
Yeah. and going
That's
further.
what I tried, and then they give you a little, they don't give anything. Below soft edges, all kinds of options that are, so this is supposed to vertical value, vertical axis. That's supposed to be it.
Did you go to the bar, the last picture?
No. Chart area, you'd think this one is not, it's not it. Outline, no. Font, chart type, template, data, move chart, bring front, send. No. Format, this one is supposed to be it. You click on it and it gives you options, but this one, there's the option that I need isn't here. Plot area options. That's not okay. I got it. Vertical axis, horizontal chart area. No.
Did you click on the bars, the last picture?
The
when you
bars.
So when you go up those images, did you click the bars?
What bars?
Outside, so under axis options is pictures, axis options.
Yeah.
On the below, is that where you, below the,
Where-
there's little 4 pictures below that.
No, I didn't see pictures. Where pictures?
He was just there, just
Yeah, just
get
one.
rid of it.
I'm sorry to hear
Ah.
Picture.
Yeah.
No, I cannot see. Okay, well, there's only way to do it is just to ignore it. Okay.
So go back to chart options.
Yeah.
Go to where you were, the vertical value.
Yeah.
Did you click on that one?
This one?
Yeah. And then axis
Axis
options.
options. Yes.
Maybe.
Thank you. So minimum bounds. Is it a vertical axis? It must be.
Maybe like negative numbers will show you.
Is there a vertical word there?
Yeah.
There is no vertical word.
Um,
I know it is, but it is definitely not something that they like this. Okay. Okay. So all right. So you can see the A. That's the red one. You see B, which is the green one. Okay. So they're visible. Now their linear combination, as written with these x and y, 1.51, is the blue one. So I even ignore that the fact that what is written there. What is the operational here is c is equal to xa plus yb. Okay, so then we solve the problem differently from what we just saw. We are trying to adjust the two weights, 1.5 and 1, in such a way that our blue vector turns. It turns brown. Not turns brown, becomes brown. Okay, so. Okay, so any thoughts of what I can do? So 1.5 is the value of the weight of A, which is red. What should I do with it? Maybe should I make it larger? Not make too large. Let's make it smaller. Okay, so it's moving in the wrong direction. So let's move. Let's decrease Y. Okay, so it's getting closer and closer to A. That's good. Increasing. See, you're following what's happening to the weights x and y, right? These are the two numbers, 1 and 1.5. I just changed them slightly in order to move in the right direction. Okay, that doesn't want to go any below this. Well, let me change the numbers so we could actually have a better. Well, my vector D is the wrong one. What is the vector D is in fact 5, 1. So I was supposed to put 5, 1 here. I'm looking for the wrong one. Okay, so that makes more sense. So the brown one is the vector D we're looking for. That is the solution, not the solution, but rather the answer. And the what we're supposed to plug in into this are x and y, and they're, as I said, the combinations of red and green one. So this one, as you can see, that if I'm increasing the weight of y, this is what is just happening, I am decreasing or increasing the weight of y. Okay? And as you can see, it is getting closer direction-wise, but then I want to, that's pretty close, right? So, so you see what has happened, right? So you see the weight, the weights are here. So the weight of vector A is 1.5. So this one, this one multiplied by 1.5, which is roughly here. The red one is here, and then I make the green one be multiplied by 0.8, which is slightly shorter than that. Then I take those two vectors here, add them together, and the result is 0.5, 0.7, which is, in my estimate, fairly close to 5.1. Okay, and so then that gives me the answer, 1.5, 0.8. Does it match what we got? 1.5, 1.8. It's fairly close. I don't think I can increase the accuracy here in order to have my numbers more precise. They're just not set to be more subtle variations. I cannot do it changes by 0.1, which is just, why doesn't it work? So hold on a second. So if I want to have x to be 1.6. So what if I just go with 1.6? See, it jumps too much. X just jumps too much. I don't know why. And this one, I want to go down, and it goes, well, okay. Now it's really close. So y is 0.6, and x is 1.5. Okay, and the solution, as you can see, has been found. So the idea is to represent the blue vector as a linear combination of red and green. And we solve the problem fairly closely to the truth. The answer is the same. Okay, so this is more complex, obviously. Even Excel has trouble with this in comparison to this, right? So this was two lines. We found the intersection, zoomed in. We have the solution, okay? Or at least we understand what we're doing here. This one is certainly more challenging. So why do we do it this way, not the other way? The reason is, well, multiple reasons, but one is the dimensions are, it is this simple, this one was simple, as well as this picture that we looked at of two lines is simple. The idea is really simple. Two lines, we find the intersection, okay? Now, but what if we progress on with dimensions? Meaning, what if we have three equations, three unknowns? Three equations, three unknowns. So three equations, three unknowns. Okay, so let's write, I don't know, x plus y minus z is equal to 7, 2x minus y plus 2z is equal to 0, 3x plus y is equal to 5. Okay, so this is my system, three equations, three unknowns. Certainly nothing outrageous about it. It's way more complex as in comparison to what we just saw, but it is not large at all. So if you look at any kind of a practical application of linear algebra, they have hundreds of thousands of equations and hundreds of thousands of unknowns. Okay, so that is just a 3 by 3. If we try to interpret this geometrically, so what is the geometric interpretation? Well, geometric interpretation, this was a geometric interpretation, right? This is what I was talking about. This is geometric interpretation. Two lines, solution is the intersection, right? We saw those lines. These are the lines. This is the intersection, okay? Now, what if we're talking about three equations, three unknowns?
Same thing, it's just three-dimensional.
What?
Same thing, it's just three-dimensional, right?
Well, yes, but so what is it?
Intersection.
Of what?
Three lines.
No. Three planes. So you can see how things starts to pile up suddenly. One step up and we have suddenly three planes in the three-dimensional space. Not two lines on the plane. We have three planes in space. Okay, they can be once again related to each other, located relative to each other in any imaginable way. And so then just try to visualize it. This is still visualizable. Okay, I could still try, not with Excel, but with something else. I could try to take the three-dimensional space, plot three planes, right? I plotted one plane once. Remember, that was a bit of a hassle. But here I would have to plot three planes, and then try to find the intersection. What it means to intersection? It's not two planes. Two planes intersect nicely, but three planes. Remember that. Remember the generic way planes intersect? They have one point in common, just like the floor and the two walls. These are the three planes, and the intersection is a single point. So it still can be interpreted, but the other possibilities are still very numerous in comparison to this case. What can possibly happen? Two lines might be parallel, then there is no intersection, or they coincide, then there are infinitely many solutions. Okay, these are the only possibilities. With planes, the planes might intersect in a very weird way. For example, well, they could still be parallel, right? So they could be parallel. They could still coincide. So the generic case is still this one, very nice, very simple, with a single intersection. So no intersection. Then you can have infinitely many. There are some exotic intersections such as this. So if you look from the side, these three will intersect like this. So they form some kind of a, what is it? I don't know, some kind of prism. It's not a prism. It is a prism. It just extended. So we're looking through it. And how many solutions?
7. Versus 3.
So each of these lines is just a plane we're looking at like this. Okay? So, well, what is the solution? The solution are all those points x, y, z that belong to all three of the planes. So, how many?
So we get whatever's inside that triangle.
No. Once again, the line represents the plane that we're looking at from the edge. So, where are the solutions?
Lines meet?
What?
Where the lines meet?
Okay,
But they do not. They meet only two at a time.
so
There are no solutions, right? So the geometry becomes more and more complicated as you go in high dimensions. But the classification remains the same, and that is one solution, none, or infinitely many. Okay, so it's just visualization. It becomes hard. I do want to now let's take this and see what it means if we translate it into a vector equation. Vector, once again, still not a matrix, a vector equation. So what does the vector equation look like? We are not going horizontally anymore, but we're going vertically. So what's the first vector? Yes, in the system, yeah. What? 1, 2, 3. 1, 2, 3. And its multiple is x. Then the next one is the multiple y. The vector is 1, negative 1, 1. And the next one, what's the last vector? Negative 1, 2, 0. And it's supposed to be equal to 7, 0, 5. So the interpretation is very different, either geometric in terms of planes or algebraic in terms of vectors. But as you can see, the interpretation is still similar to what we had. This is still a linear combination. Okay, and once again, what we're looking for, so find a linear combination that of vectors, these vectors say A, B, C, in such a way that they together, that combination is equal to the vector we're looking for, 705. So in that sense, it's the way we describe the problem is exactly the same. So take the coefficients, form vectors, and then create a linear combination, vary x, y, and z. Okay, so that way the three vectors will be lying in three-dimensional space. Instead of having one vector, instead of having two vectors as here, green and red, we'll have the third vector. And once again, we'll be varying three weights for each of the vectors, each of which, and then together it will give me a new vector, and hopefully I'll tweak it a little bit so that I will end up with my answer, okay, which is 705. Okay, so the plan is the same, but certainly it is more algebraic, and it is, well, the main thing is really not that it is how it's going to work out, we'll see, but it is different. So the approach is very different between these geometric and algebraic interpretations. Okay, so we'll revisit that. Linear combinations will be reappearing again, but really what we want to do and spend some time doing is finally getting back to matrices and looking at the matrices in all dimensions. So this picture, the computation at the top, it tells you pretty much the whole story, and that story is multiplication of a matrix 2 by 2 by vector, which is 2 by 1. So let me carry this out one more time, and then I'll do the three-dimension too. So vector is, say, 1, 1, 2, 3, multiplied by, it doesn't matter. I mean, that equation was just an example of where this stuff comes from, but multiplication works out specifically with any entries that you choose to have. So -1, 2, and how does it work out? Well, remember, this is how it works out: 2 by 1, and this one is 2 by 2, and this is 2 by 1. Then the answer, when you do carry out that multiplication, this is, you cancel these, and the answer then becomes 2 by 1. So then you know that you're gonna judging by that, like this, from the matrix and the second vector, you write the dimensions, then you figure out the dimension of the output, which is 2 by 1, and then you write it, and so you know that you're gonna need two entries. You're going to need two entries, and you find those two entries by the way we talked about, through what amounts to dot product. Okay, so then if I want this one, I take this first row, first column. Well, there's only one column in the second one, but it will be 1 times -1 plus 1 times 2. So the answer is -1 plus 2 is equal to 1, so I will end up with 1 over here. And second, I take the second row and the same column here, because there's only one. 2 times -1 plus 3 times 2 is equal to -2 plus 6 is equal to 4. And so I have my 4 over here. So that is multiplication of a matrix by a vector. But matrices can be multiplied themselves. So we're gonna do that next. All right. See you tomorrow.